Hello students, in this video we'll discuss finite rank and finite genus entire functions. Let f map c into c be an entire function with zeros or roots a1, a2, an. We say that f has rank p if the sum n goes from 1 to infinity of the modulus of an to the negative p minus 1 is less than infinity. Good, right? And so two sort of caveats behind this, right? So one caveat is, just as a remark, note, we will say that f has rank 0 if f is a polynomial. In other words, if there is going to be only a finite number of terms over here, and polynomials are entire functions. And infinite rank if no p works. Now we can think back to Calc 2, right? In Calc 2 we know sequences for no value of p will that the sequence a and converge. An example of an infinite rank, so example of infinite rank would be if I look at the zeros that are going to infinity very, very slowly, right? So if an was equal to the log of say like maybe just to shift everything 100 plus n, then what do we know? Then we know the sum n goes from 1 to infinity of an to the negative p minus 1 is infinite for all p and n. So this would be an example. That's an entire function where the zeros are going to infinity so slowly it won't be finite rank, it'll be infinite rank, okay? So there's phenomena that happens like this, right? Good. So that's what it means to be finite rank p, okay? Now when f has finite rank, we can form the standard part, this is called the standard part of f of z, as what? As just this part of the Weierstrass product. N goes from 1 to infinity of e p z over a n. And the p here is fixed, right? The p is just whatever the rank is, right? And we know this will converge by exactly by this condition over here, right? So where these EP are, of course, the canonical factors, right? So EP of z, we can recall, is just 1 minus z, and then e to the z plus all the way down to z to the p over p. Excellent, okay? Or the canonical factors. Weierstrass factors. Excellent. Okay, that's what needs to be finite rank. Good. Now, of course, we want to talk about genus now because this is only one part of the entire function, right? So we know, so recall from the Weierstrass theorem, the Weierstrass factorization theorem, gives what? Weierstrass factorization gives that f of z is going to be z to the power m if there's a root at 0, for example. And then e to the g of z times this product over here. N goes from 1 to infinity. Now, by this assumption, we can say that this is going to be EP, this is the standard part, EP of z a over n. Good. And so now, of course, what's Weierstrass tells you what? Weierstrass tells you that this g of z and here, g of z is an entire function. Good. Now, of course, what would be great? It'd be great if g of z was a nice entire function, like a polynomial, right? So in the case when g of z is a polynomial, we say that f has finite genus. Okay? And so what's the genus? The genus of f of z is defined by call it fancy g. It'll be the maximum of the degree, let's call it g tilde. That's the genus is, because I already have g over here in my polynomial, right? It's the maximum of the degree of g, the degree of the polynomial and the exponent over here, or this p over here. Okay? So we're very used to, one of the classic examples we know of something that has finite genus is something that a canonical product we already know, right? So if you recall that the sign of pi z is pi z times the product, and goes from 1 to infinity, of 1 minus z squared over n squared. Well, what are the roots of sine of pi z? The roots of pi z over here are just the integers, right? So if I choose p equals 1, if p equals 1, that will work, right? And so the genus of sine, so this has genus equals 1. Excellent. Of course, you can have infinite genus, right? The whole point behind infinite genus is you can look at something that looks like what? That looks like e to the z, right? E to the z is not a polynomial, but it fits this form because it's the exponential of an entire function, because the exponential is entire. So if I have e to the z, that's not a polynomial. So that means that the maximum of this thing is going to infinity. So that'd be an infinite genus thing, right? So when you start to concatenate higher order exponentials, not bounded by a polynomial, that's when you get into problems, right? So in other words, we want to consider things that have these sorts of growth conditions where the Weierstrass product is under control, where the Weierstrass product corresponds to just one particular fixed value of p over here, and I don't have to systematically increment that up to sort of tame whatever sort of ill-posed sequence of roots that I have. So we're very carefully will analyze these things, and this will give rise to the idea of now we have rank, we have genus, and next we'll talk about order, right? And order is an estimate, and all these things are basically turn out to be very, very closely related to each other. And it will prove the Weierstrass factorization theorem, which gives us all sorts of really useful facts about the range of entire functions. Thank you very much.